Welcome to Math 201, Lesson 3.7 on implicit differentiation. Today we learn the technique of implicit differentiation, which is used when the equation for a curve is not written in the explicit y equals stuff with x's format. So an explicitly defined curve is probably what you're much more used to seeing. It has y equals and then a bunch of stuff with x's on the other side. So this one is a polynomial and there's its graph. An implicitly defined curve does not fit this format, y equals stuff with x's. So the x's and y's are sort of all jumbled up on both sides of the equation. So this is 9x squared plus 4y squared equals 25, and its graph is that of an ellipse. Okay, before I jump into our first example, I want to just do a little side note here about the chain rule. So if I want to take d dx of x squared, okay, we can think of that as the derivative of some stuff squared. It's just that my stuff is a plain old x, right? So when I do the power rule, it's bring down the 2, copy the stuff, reduce the exponent by 1, and then multiply by the derivative of the stuff, okay? And this comes out to 2x times 1, which is 2x. Okay, so when the stuff is just an x, we don't actually write down the chain rule, even though we're doing it. Okay, so the derivative of x squared, that's some stuff squared. So the derivative of some stuff squared is 2 times the stuff to the first times the derivative of the stuff. But the derivative of the stuff is just 1. When the stuff is just an x, the derivative of the stuff is 1. So we're doing the chain rule even though we're not thinking about it, even though we're not writing it down. All right. Now, if I want to take d dx of y squared, this is the derivative of some stuff squared again. So I'm going to apply the chain rule and I'm going to bring the 2 down, copy the stuff, reduce the exponent by 1, and then multiply by the derivative of the stuff, which is y. So this comes out to 2y times d dx of y is not 1, okay? d dx of x is 1, okay? Because the variables match. The derivative with respect to x is 1, okay? But the d dx, the derivative with respect to x of y is not 1. That's dy dx, right? That is dy dx or y prime. Okay, because y is a function of x, right? Think of y as a function of x. Okay, so, or an f of x. So when you take its derivative, it's not just 1, it's whatever the formula is. It's whatever dy dx is or y prime is. Okay, so that's a little primer for implicit differentiation. Let's look at the graph of 9x squared plus 4y squared equals 25. It's an ellipse, and I want to find a formula for dy dx. So I'm going to start by taking d dx of both sides of the equation. So this is a trick we learned in our previous section when we were taking derivatives of inverse functions. We started with a true equation and we took d dx of both sides. So I can use that technique here as well to try to solve for dy dx. Okay, d dx of 9x squared is 18x. That's 9 times some stuff squared. So 18 times the stuff times the derivative of the stuff, which is 1. Okay. And then for y squared, that is 4 times some stuff squared. So I'm going to apply the power rule and I'm going to get 8 times the stuff times the derivative of the stuff. The derivative of y is y prime. It's not 1. The derivative of x is 1. Okay, and then d dx of 25, that's 0. The derivative of a constant is always 0. Okay, so now what I want to do is solve for y prime. So this says 18x plus 8y prime equals 0. I just want to solve for y prime, get it by itself, because y prime is just another notation for dy dx. So let's get y prime alone, and I'll have it. I'm going to subtract 18x from both sides. So 8y prime equals negative 18x. Divide both sides by 8y, and we get y prime equals negative 9x over 4y. Now let's use that formula we found for dy dx to find the equation of the tangent line to the ellipse at the point negative 1, 2. So that is this point right here. And the tangent line is going to look something like this. And if I know that dy dx represents the slope of a tangent line, I could calculate a numerical slope because I know the point. So the slope of this line is going to be dy dx, the derivative, evaluated at the given point, negative 1, 2. So it's going to be negative 9 times negative 1 over 4 times 2, which is 9/8. Okay, I can't tell what the y-intercept of this line is. It looks like it's really going to be close to 3, but you can't tell based on a sketched graph. So I'm going to try to figure out what it is. I'm going to use point slope form for the equation of my line. Y minus y1 equals m times x minus x1. And my point, that's your x1, y1. Okay, so this is going to be y minus 2 equals 9/8 times x minus negative 1. And I can now solve for y, just get y by itself. I'm going to have y equals 9/8 x plus, so I'm distributing this 9/8. So I get 9/8 x plus 9/8 plus 2, because I have to add this 2 to the other side. So I have 9/8 plus 16/8, which would be 25/8, which is very close to 3, okay, because 24/8 would be 3. So 25/8 is very close to 3. So that seems like it's right. Part C, we want to find both graphically and algebraically all the points on the ellipse with horizontal or vertical tangent lines. So I have vertical tangent lines here and here, horizontal tangent lines here and here. Vertical and horizontal. And I have a formula for dy dx, the slope of the tangent line at any point x comma y. And places where the tangent line is horizontal, okay, that happens when your derivative is 0. So that happens when dy dx equals 0, which happens when negative 9x over 4y equals 0, which happens when x is 0. Doesn't matter what y is. If x is 0, that whole fraction is going to be 0. So when x is 0, I have horizontal tangent lines, and I need to know the y values. I could get those from the original equation, right? The original equation of the curve was 9x squared plus 4y squared equals 25. And I'm going to put in x equals 0 and find out what the y is in those locations. So 9 times 0 squared plus 4y squared equals 25. So y is going to be the square root of 25 fourths, so 5 halves, plus or minus 5 halves. So this point right here, one of my horizontal tangent lines is at 0, comma 2.5, or 5 halves. And my other one down here is at 0, comma negative 2.5. Okay, and I'm out of room, so I'm going to repeat this process for the vertical tangent lines on the next slide. Okay, now I'm going to look for the locations of these vertical tangent lines. Um, and vertical tangent lines have an undefined slope. So I'm looking for places where dy dx is undefined because vertical lines have an undefined slope. So negative 9x over 4y would be undefined when the denominator is 0, when 4y equals 0, or when y equals 0. Okay, and then I already knew that, right? This point is something comma 0, and this point is left comma 0. So to find the x values, I'm going to take the original equation, 9x squared plus 4y squared equals 25. I'm going to replace the y with a 0 and solve for the x. So I have 9x squared plus 4 times 0 squared equals 25. So x is going to be plus or minus the square root of 25 ninths, or plus or minus 5 thirds. So this point right here is going to be 5 thirds comma 0. And this point is negative 5 thirds comma 0. If you have an equation that you cannot solve explicitly for y, we say that equation defines y implicitly. And the technique we used above is called implicit differentiation. How do you know when you need to use it? The equation has the x's and the y's all jumbled together instead of having y equals on one side and all x's on the other. When you're differentiating implicitly, the key is to remember that whenever you're taking the derivative of a term with a y in it, when you use the chain rule, you're going to multiply your derivative by dy dx instead of just by 1. So we've reached our activity for section 3.7. I want you to pause the video, take some time to work through these problems on your own, come back and watch the video solutions when you're ready. For each graph of the equations or graphs shown below, complete the following. 1, sketch where the tangent lines are horizontal or vertical on the graph. Find dy dx by implicit differentiation. And 3, use dy dx to algebraically determine all the points on the graphs with horizontal and vertical tangent lines. So we'll start with this equation for a circle, x minus 2 squared plus y minus 1 squared equals 1. So this is a circle that has its center at 2, 1, which means I can find all of these points where the tangent lines are horizontal and vertical, because I know the center of the circle and I know its radius is 1. So this point is 3 comma 1. This point is 2 comma 2. This point is 1 comma 1. And this point is 2 comma 0. So I found the points where all the tangent lines are horizontal or vertical, but now I'm supposed to solve for dy dx and algebraically find those points. So to solve for dy dx, we take d dx of both sides of the equation. d dx of x minus 2 squared plus y minus 1 squared equals d dx of 1. Okay, so I'm going to take the derivative of this term by term. This is some stuff squared. So I'm going to bring down the 2, copy the stuff, reduce the exponent by 1, then multiply by the derivative of the stuff, d dx of x minus 2. Okay, and then I'm going to repeat on this next term. So this is some stuff squared. So I'm going to bring down the 2, copy this stuff, reduce the exponent by 1, then multiply by the derivative of the stuff. And then that should equal, sorry, I ran into my graph here. That should equal 0 because d dx of 1 is 0. Okay, so now I'm going to calculate these two d dx's that I left in my equation. I've got a d dx of x minus 2 I need to figure out, and a d dx of y minus 1. All right, so 2x minus 2. So this is 2x minus 4 times the derivative of x minus 2. Well, the derivative of x is 1, and the derivative of negative 2 is 0. So that's just a 1. And then I have 2y minus 2. And then I have to multiply that by the derivative of y minus 1. Now, d dx of y is not 1. It's y prime. It's dy dx. So the derivative of y is dy dx, y prime. And then d dx of negative 1 is 0. Now I just have to solve this equation for y prime. So I just want to get y prime by itself. I am going to subtract 2x and add 4. So I have 2y minus 2 times y prime equals 4 minus 2x. And then I'm going to divide both sides by 2y minus 2. So I have y prime equals 4 minus 2x over 2y minus 2. And there's my derivative. And then I want to use that to confirm where my tangent lines are horizontal and vertical. So for horizontal, I'm looking for places where y prime equals 0. So that would happen when the numerator of a fraction is 0. The only way a fraction can equal 0 is when its numerator is 0. So if I solve this for x, I get 2. X equals 2. And you can see that that is the case, that I have horizontal tangent lines when x equals 2. One here and one here. Both of them have an x value of 2. To get the y value, I need to use my original equation. So I would plug into x minus 2 squared plus y minus 1 squared equals 1. So I'd have 2 minus 2 squared plus y minus 1 squared equals 1. That's just 0. And this is going to be a quadratic equation. So I have y minus 1 equals plus or minus 1. So y equals 1 plus 1 is 2, and negative 1 plus 1 is 0. So my points are going to be 2 comma 2 and 2 comma 0. And I'm out of space for horizontal. I'll go to the next slide for vertical. Okay, I've rewritten the original equation of the circle and the formula we found for y prime. And I want to find out when my tangent lines are vertical. Okay. And vertical tangent lines happen when the derivative is undefined, which would happen when its denominator is 0. And that would happen when y equals 1. And to find the x values that go with that, we're going to plug into our original equation. X minus 2 squared plus 1 minus 1 squared equals 1. That's just a 0. So x minus 2 is plus or minus 1, just square root both sides. And I get x equals 1 plus 2 is 3, and negative 1 plus 2 is 1. So my points are going to be 3 comma 1 and 1 comma 1. And you can see that those are the points on the graph if you go back a slide and check it out. Next, I want to look at this parabola. Y squared minus 1 equals x. It's a parabola that opens right. It looks like there's only one point that's interesting. This one right here has a vertical tangent line. So that's the point I'm going to be looking for. I'm going to start by finding dy dx. I'm going to take d dx of both sides of this equation. Okay, and this is the derivative of some stuff squared. So I'm going to bring down the 2, copy the stuff, reduce the exponent by 1, then multiply by the derivative of the stuff. And then The derivative of -1 is 0, so that goes away. And that equals d dx of x, which is 1. So this is 2y prime equals 1. And to get y prime alone, I'm just going to divide both sides by 2y. So there's my formula for y prime. It's 1 over 2y. And there are no places where the tangent line would be horizontal because horizontal tangent lines happen when y prime is 0, but that would never happen because the only way a fraction can equal 0 is if its numerator is 0 and this numerator is 1. Okay, so we have no horizontal tangent lines. But for vertical tangent lines, those happen when the derivative is undefined, which in this case would happen when the denominator is 0. So that happens when y is 0. And to find the x coordinate that goes with that y value of 0, plug into the original equation. So I've got 0 squared minus 1 equals x. So x is -1. So this point I'm looking for is at -1, 0. Okay, for our last example, we're going to look at an ellipse. X squared over 9 plus y squared over 4 equals 1. And it looks like there are 4 locations that I am looking for the coordinates of those points. 2 that have a horizontal tangent line and 2 that have a vertical tangent line. I'm going to go ahead and take d dx of both sides. Instead of writing x squared over 9, I think I'm going to write 1/9 x squared. Just makes using the power rule a little bit easier. And then 1/4 y squared equals d dx of 1. Okay, the derivative of 1/9 y squared is, sorry, 1/9 x squared is 2/9 x times the derivative of x, which is just 1, okay, which we don't usually write down. I'm only writing it down to remind us that in the case where it's the derivative of y, like in this case, I have 1/2 y times the derivative of y, which is not 1, it is y prime. And then that equals d dx of 1, which is 0. Now I just want to solve for y prime. So y prime is going to be -2/9 x divided by 1/2 y. And I could simplify that by multiplying the top and bottom of this fraction by, well, I'm not going to multiply the top and bottom. I am going to, instead of dividing by a fraction, I'm going to multiply by its reciprocal. So y prime is going to be -2x over 9 times 2 over y, which is -4x over 9y. Okay, so where are my tangent lines horizontal? That would happen when y prime is 0, which happens when the numerator is 0. And when is my tangent line vertical? That happens when y prime is undefined, which happens when the denominator is 0. So horizontal tangent lines happen when the x coordinate is 0, so 0 comma something, and this point down here is 0 comma something. And then my vertical tangent lines happen when the y coordinate is 0, so something comma 0 and something comma 0. To find the somethings, I use the original equation. Um, and I'm out of room, so I'll go to the next slide. Okay, I've jotted down the information that I already had. I know that my horizontal tangent lines happen when x equals 0, and my vertical tangent lines happen when y equals 0, and I need to find the associated coordinate. Like for these x equals 0s, what are the y's? For these y equals 0s, what are the x's? So you use the original equation to find them. So when x is 0, I have 0 squared over 9 plus y squared over 4 equals 1. So that's just a 0, and I get y squared equals 4, so y equals plus or minus 2. So my points are 0 comma 2 and 0 comma -2. That's where my tangent line is horizontal. And then for vertical, my y is 0. So I'm going to have x squared over 9 plus 0 squared over 4 equals 1. And when I solve this for x squared, I get x squared equals 9. So x is plus or minus 3, which means my points are 3 comma 0 and negative 3 comma 0. Those are the points where the tangent line is vertical.